Hey Team Bio, welcome to your first of a 4-part series on organic compounds. Sorry again about the length of the screencast that you had to watch for homework last night. I promise this one will be much shorter. Okay, organic compounds. We have discussed the big 4 organic compounds. You also hear the word BIMs thrown around, biologically important molecules, but typically I refer to these different organic compounds as the big 4. Okay, so we're starting with carbohydrates. For no particular reason. Okay, so here I have 2 very different pictures, which both are showing you carbohydrate. You are probably very familiar with this form of carbohydrate. This is carbohydrate primarily in the form of starch. But what you might not know is that a lobster shell is also composed of carbohydrate. This carbohydrate is called chitin. Chitin is made up of glucose, a special type of glucose that contains nitrogen. It's called an amide derivative of glucose. And it's actually the second most abundant polysaccharide that's found in the entire world. So this is just to show you that carbohydrates can take on a very diverse arrays of structures and give a very diverse arrays of functions. Not the definition of a carbohydrate, but the way that carbohydrates are generally recognized is that they typically contain carbon, hydrogen, and oxygen in a 1:2:1 ratio. So our most famous form of carbohydrate, glucose, is C6H12O6, and you see that it follows this pattern of 1:2:1, and this is obviously glucose. These hydrogen-oxygen bonds that form within carbohydrates are polar bonds. So as a result, this is not always true, but often carbohydrates are hydrophilic. Hydro meaning, I'm going to do that better. Hydro meaning water, and philic meaning loving. So many of these organic compounds are water-loving compounds. They are very water-soluble. They readily dissolve in water. They readily bond to water molecules because of these polar bonds in the hydrogen-oxygen bonds in these organic compounds. Okay, so carbohydrates have a diverse array of functions in cells. They have structural functions. As you see in the example above, chitin is a structural carbohydrate, and then cellulose, which makes up the majority of plant cell walls. We're going to see an example of that down below. This is cellulose. So they play a structural role in many cells. They're used for energy. And typically, the form of energy that they provide is quick, or not CH, quick, CK, or short term. So if you're going out for a long run and all of a sudden you bonk, you've run out of your carbohydrate reserves. The last major function that they play in cells is cellular identification. Often on the outside of cells, different cells might be tagged with different sugars, or different proteins are tagged with different sugar groups, and that serves as like a little molecular flag. I guess I'll write that down. Which can tell other cells what type of cell or what type of protein on this cell this is. Okay, so structural, energy, and identification are all the major functions of carbohydrate. Okay, as I said in our last screencast, or 2 screencasts ago, we can break up all of our big 4 biomolecules into monomers, which is our most basic building block of a organic compound, and then a dimer would be 2 of the same organic or different same type of organic compound, and then a polymer or polymer is 3 or more. So this is 1, this would be 2, and this would be 3 plus. For carbohydrates, we have a specific name for monomers of carbohydrates. It's called a monosaccharide. CCHARIDE. A monosaccharide is one monomer of carbohydrate specifically. So some great examples of monosaccharides are glucose and fructose. These are kind of the shorthand chemical formulas for these 2 molecules. Interestingly enough, they have the exact same chemical formula. If you were to count up the number of carbons, hydrogens, and oxygens in these 2 compounds, you would see they're both C6H12O6. But the way that the compounds are, or the elements are strung together, they take on slightly different shapes. You'll notice that glucose is a ring that has 6 sides, and fructose is a ring that has 5 sides. So the same chemical formula, but different structural arrangements are called isomers. Formula, diff, structural arrangement. Okay, and the different structural arrangements of glucose and fructose actually has a profound effect on a lot of their different properties. One of the most striking for humans is that when you eat glucose and fructose, they have a very different perceived sweetness. Fructose is perceived to be much sweeter than glucose. Which is why we enrich it. We enrich things for fructose when we want to sweeten them, like, for example, high fructose corn syrup. Okay, so that is our monomer of carbohydrate. Our monosaccharide is, or our 2 monosaccharides are glucose and fructose. They're the most basic units of a sugar. Okay, a dimer of a carbohydrate is called a disaccharide. And our example of a disaccharide here is glucose and fructose put together through a reaction that we're going to study later on in this unit. And this compound is sucrose, or table sugar. So sucrose, which is a disaccharide, is composed of two monosaccharides, glucose and fructose. There is a special reaction we're studying later on we'll learn brings these glucose and fructose together to make sucrose. Another example of a dimer, a carbohydrate dimer, would be lactose. Lactose is composed of glucose and another monomer called galactose, and people who are lactose intolerant lack the enzyme to break this dimer into the two monomers. So they are unable to break the disaccharide glucose into its monosaccharides, glucose and galactose. Okay, and moving on down to our polymer of carbohydrate is called you guessed it, a polysaccharide. Okay, we have three important examples of polysaccharides, which are all polymers of glucose. The first is starch. Starch is how plants store carbohydrate energy. So if you look at any storage facility for plants that's storing carbohydrate energy for them, they will be starchy substances. So for example, potatoes are chock-a-block full of starch, as they are an energy storage facility for the plant. Okay, so this polysaccharide starch is actually composed of a bunch of glucose monomers. So this is one monomer of glucose. And they're all strung together to make the polysaccharide. Animals store carbohydrate energy in a slightly different form from plants. We store it as glycogen. Glycogen is also composed of glucose monomers. But the way that glycogen forms a polysaccharide is through these branched chains of glucose. So starch is always found in long, straight, linear chains, but glycogen is going to be forming branching chains. So this is how animals store carbohydrate energy. And then the last form of a polymer that we see here is cellulose. Now, cellulose provides structural support for plants. So, unlike starch and glycogen, which were performing the function of short-term or quick energy storage, cellulose is providing structural support, so it has a different function. It's actually the most abundant polysaccharide on Earth, and it is also indigestible to animals. Even though these are just glucose monomers strung together, animals cannot break the bonds here between these glucose monomers. So animals that consume a bunch of plant material often have a very complex digestive system that hosts a whole diverse array of bacteria living in their gut that actually help them break down the cellulose and do the digesting for them. So, for example, cows, as you know, often they have a couple 7 stomachs, I think, and they regurgitate their food and then they re-chew it to break it down into smaller bits to make it easier for the bacteria that are living in their digestive system to break down the cellulose for them. Okay, so cellulose forms these long straight chains that are held together by covalent bonds between the hydroxyl groups here. But then you'll also notice that there are these dotted lines, which I'm going to highlight some of them here. So the dotted lines are actually showing hydrogen bonds that hold the chains of cellulose to one another, providing kind of a rigid mesh, giving a lot of structural support. So cellulose is held together both by covalent bonds between the glucose monomers as well as hydrogen bonds between the different glucose chains one another, and also there are some hydrogen bonding that occurs within the chain as well. So that provides a lot of the structural integrity of cellulose. Okay, that is all. See you in class tomorrow.